Okay. So I'm going to talk about inverse adding doubling. It turns out I have opinions about it, and um, they're strongly held opinions. I'd like to remind you of this quote from Einstein, is that a theory is something that nobody believes except the person who made it. So, you've sat through Voss's lecture, you saw all the diffusion, you go, I don't really believe that stuff. It's like, but Vossen does. Um, and an experiment is something everybody believes except the person who made the measurement, because you go, oh, I know all the gory details. I know what I did wrong. I know I used the wrong ruler. I don't know. So this whole inverse adding doubling is a combination of experiment and theory. And so long ago, I actually wanted to measure optical properties because I thought it was important and people cared. I was disabused of this notion that by many people, that for a variety of reasons, and mostly because the people who care about optical properties tend to be engineers, and they want to figure out something. The doctors, they care about physiologic parameters. They don't care about optical properties so much. And so the most successful biomedical optics devices are pulse oximeters, right? And they don't tell you anything about the optical properties. They just give you the O2 sat for blood. So to make optical properties, I knew I didn't want to have to rely on a lousy model like diffusion theory, which I'd spent a lot of time on working on. I want something that worked all the time, so that there would be no excuse about the model being the weak point in the measurements thing. And then if it didn't work, I could confidently blame the experimentalists, because I'd say the model's perfect. It's like accurate to 5 places. How could it go wrong? And the only way it could go wrong is if you gave it bad measurements. So whatever model I used had to work for all optical properties. So all mu sub A values, all mu sub S values. None of this nonsense about diffusion approximation only working in highly scattering media or far from the sources and light sources. It had to work for all anisotropies as well. And it had to work with mismatched boundaries, because we seldom measure things underwater. So based upon not my postdoc, but my PhD work, I had developed a Monte Carlo model, and I had implemented adding doubling. And so I said, both of these are accurate for all these cases. They'll work for any set of optical properties, any set of mismatched boundaries. And the basic idea is trivial. You measure something, you guess some optical properties, you calculate what you measured, you compare them. If they're the same, you're done. If they're not the same, you do it again and you keep going. So we're brute forcing the problem. We're not actually inverting the radiative transport equation. We are just iterating it until it capitulates. There's a bunch of implicit assumptions in the adding doubling theory. It's one-dimensional. I'll talk more about that. I don't worry about polarization. You can stick polarization in if you want, but usually it's uninteresting. The layers are uniform. You don't get to have variations in the optical properties across. It's time independent, so it's steady state. There's no time dependency, and it uses Henny-Greenstein scattering. This can be loosened, so you can put in me scattering, but then it becomes computationally much harder. So the implicit assumptions for experiment is that you match theory and you don't make lousy measurements. You're careful. I wonder if this is actually the talk I want to give. Yeah. So one thing that I was early on interested in is are there unique solutions? You know, if you measure reflection and transmission, will that give you a unique set of absorption and scattering values? And this grid kind of says that, yes, you get unique values. So in this case, we have a sample, we have 10% unscattered transmission, which means that we know what the total absorption and scattering coefficients are, the sum of the two. And then we can vary the anisotropy from -1 to 1. And we can vary the albedo, which is basically the ratio of scattering to total interaction. So when the albedo is 1, it's completely white. When the albedo is 0.5, it's 50% scattering and 50% albedo comes from astronomy, where they talk about the albedo of planets. And as something becomes white, then it becomes has an albedo of 1. Also, albedo comes from albumin, right? As you put the white of an egg is all albumin. You put it in the pan, it turns white, and that's so it's all consistent, at least out with albedo. So I chose to not use Monte Carlo. I chose to use adding doubling because adding doubling was much faster, and you could get 5-place accuracy in, you know, say 1 second, as opposed to Monte Carlo. To get 5-place accuracy at the time, you'd have to wait a few hours. Since then, others have said, this adding doubling is just too complicated. I'm just going to do Monte Carlo. And so there are inverse Monte Carlo models, and then there's inverse adding doubling. And the inverse Monte Carlo models seem to work just fine. Just the solutions for the radiated transport equation, the numerical solutions, it's basically an expansion of spherical Legendre polynomials. So you have, in diffusion, you have 2 terms. In P3 approximation, you have 3 terms. And in adding doubling, you have n terms. So it's, you can make it as arbitrarily accurate as you want, as long as you include a large enough number of terms. So more terms is more accuracy. Van der Hulst published this in 2 books. He has the 2 books are the first book is nothing but isotropic scattering. The second book has Henny-Greenstein scattering. He cared about radiative transport in clouds. So his 2 books do everything, but it's all assuming that there is no index of refraction mismatch. There's, clouds are same index of refraction as air, our non-cloudy air. So he didn't worry about that. And in my PhD, I implemented adding doubling, basically following Van der Hulst's, but I never got around to doing mismatch boundaries because turns out it was hard. So I wasted my year of postdocing adding mismatch boundaries so that now I could say that I could calculate these things accurately. And the bottom line is I had to break up an integral into 2 regimes. The one integral that goes over the cone that is within the critical angle, and the other is the cone that's outside the critical angle. And by doing this and then choosing your quadrature right, you could you get very accurate solutions with mismatched boundaries. How did I know I was right? I compared it to Monte Carlo. So it's this whole thing of verification is constant. You're constantly saying, is this right? Is it wrong? So as I said, adding doubling is one-dimensional, no x or y variation, just in the z. So we have uniform illumination of a slab, and z is going into the slab. So how does adding doubling work? The idea is that if you have a very thin layer, you can say, oh, I have single scattering in that layer, because you don't have to worry about multiple scattering. That's the problem, is the multiple scattering. By single scattering, we know what the phase function is, so therefore we know exactly how the light is going to propagate. And what you can do with this is, for every incident angle, you can calculate the light that's transmitted at all at all angles inside on the other side of the slab. And you can do the same thing for all angles coming back out of the slab. So you have the reflection and you have transmission. So you have reflection and transmission matrix. And for example, if you have a 1, 2, 3, 4, 5, 6, 7, 8, if n equals 8, you have your cosine of your incident angle is 1. This is perpendicular coming right on down. And this is a reflection matrix. So there's going to be different reflectances coming out at every angle coming back out. And you can calculate those out because you know what single scattering is and you're able to do it. And the same thing, so you can do that for all the incident angles. And so you have this matrix that fully describes the reflection for that one thin sample, for that one thin layer. You also have one of these that describes the transmission for that. And you say, thank God for Van der Hulst, who came up with the equations to, these are all matrices now. And, it looks a lot like the transmission through 2 layers is the transmission through the second layer and the transmission through the first layer. And then this is an inverse, so it's 1 minus r squared. So it's just like you would calculate as if you had scalars, but there's a whole thing for how to add layers together. And so the thing to do is you start off with these very thin layers and you double. You keep doubling until you get to your final thickness that you want to have. So it's pretty straightforward. And then after that, so you double until you're done, and then you add the boundaries. So there's also reflection and transmission matrices for your boundaries. So if you have, and they're diagonal in this case, because you don't, a Fresnel boundary, you don't have light coming in at this angle and then coming off at some other angle other than the angle of reflection, right? Right? Yeah.
Yeah, in this model, how do I understand reflection? Because looks the light just propagates through these 2 layers. I mean, you can add more layers, but
oh yeah, so
make a U-turn and get back.
So here you have let's just pretend this is the total reflection matrix for all these angles. How do we get something observable out? Like what is the total reflection? And these angles are chosen cleverly based upon Gaussian quadrature. And so we can then multiply each of these by a weight, and then we can integrate over all angles coming out. So we can get the total reflected flux coming out, or the total reflected flux count going down. We can do a double integral, so we integrate over all possible incident angles, And then we see what the total coming back is. So that would be like for diffuse light incident, and you can figure out what the result is for diffuse light. If you're only interested in light that's coming directly down, then you only have to worry about this column instead of doing all the columns.
Okay, I think you have to like double the number of layers to get a
Oh yeah, this is a very thin layer. You keep
Yeah.
doubling until you get the final thickness that you want.
final thickness.
Physical
okay.
thickness, right? So this
Okay.
could be, I don't know, 0.01 millimeters. And your final thickness is 2 millimeters. So you're going to go 0.01, then you go 0.02, then you go 0.04, and
Okay.
and you choose your initial thickness so that it's when you double it, it comes out right.
So okay. So I think this method actually applies to different thickness instead of just a semi-infinite thickness
No, yeah,
scenario,
you can
right?
have any thickness you want. You can do it until it stops changing, in which case it's semi-infinite, and you can have different optical properties in each layer if you want, and combine them. And
That makes sense. All right, thanks.
About the matrix algebra on the next slide, could you repeat what the indices mean?
so this is assuming you have surfaces 0, 1, and 2.
Okay.
Right? So you have your top layer 0, 1, and then you go from 1 to 2 is the second. So this is the transmission matrix go from 0 to 1. And this is the transmission matrix to go from 1 to 2. These, if we're doing doubling, then these are identical. So we're taking the same layer and doubling the thickness. So the transmission for those two is the same. The reflection are the similar. So this is the reflection for going from face 1 to the top layer, and this going from 1 to 2. So
Thank you very much.
keeping them straight's a nightmare.
How do you get a reflectance from 1 to 2? I imagine 2 to 1. What do you mean by reflectance from 1 to 2?
Yeah, if they're isotropic, then it doesn't matter.
Okay.
But if you have different layers with different optical properties, then the transmission going one or the reflection
Oh, it's
going
a
one way
refractive.
is different from the other way. So
Got it.
these are the general equations. You can make a few assumptions to simplify. If you have clear boundaries where these then tend to be diagonal, then you can make more assumptions. But you don't care about these because you're never going to use them. Trust me, you'll never need them.
Other
Well,
questions?
maybe. Okay, so I talked a little bit about the observables. That's what we're going to start with. We need to observe something, and that's what we're going to match. And the question is what will we match? And the critical idea is that if we have a laser beam hitting a sample and we measure the reflectance, it is exactly the same as if we have uniform illumination over the whole thing, and we have reflection from each of these, because this has, it's a total of 3. This is 3R. You take and divide the incident by the, or the reflected by the incident, and you get R. You get the total reflection. So the fact that we have a laser beam hitting our sample is just fine, as long as we collect all the light coming back. That makes sense? Because we do the same thing for transmission. We have our incident transmission, and we get some value t, but we could uniformly illuminate and then get the same thing. You can also, this is all for normal illumination. You can do diffuse illumination, but I'm not going to talk about it because it's a headache. It's a headache experimentally, and you don't get as good a results. And then finally, we have absorption, scattering, and anisotropy. And so that means we need 3 measurements. And the third measurement that is an obvious one is to figure out how much light gets through the sample without having been scattered or absorbed. We have some uniform diffuse. This may be strongly peaked, but there's going to be some unscattered light as well. So, and as you know, if it's completely unscattered, then it's going to be attenuated as minus mu sub t times d. So, and if mu sub t is, say, 1% per millimeter, and d is 3, 5, so you have a 5 millimeter thick sample, then this exponential becomes e to the minus 5, and it becomes quite small, and it becomes very hard to measure. And you always have the diffuse light here that is significant. So measuring unscattered transmission is hard. But if you have 3 measurements, if you have R, T, and TU, then you can guess your optical properties. You calculate those, and you say, are they the same? And if they are, then you're done. More likely is you'll just have your total reflection and total transmission measurements. Because the collimated transmission measurement is very hard to make, you need a laser. Usually you want to do broad beam or broad spectrum stuff. So you're using a lamp of some sort. Unless you have a continuum laser, you can't really do the unscattered transmission. So very commonly, you can just say, I don't care what the anisotropy is. Just let it be 0 or 0.9, and nobody will argue with you. It's like, okay, you could have, but once you have fixed G, then you have 2 free parameters to match these 2 observables, and then you can calculate what mu sub A and mu sub S are. Sometimes you're just making measurement on an arm, and you're not going to get a transmission measurement. You're just going to have reflection. So in that case, you're going to either fix the anisotropy and the scattering, or the anisotropy and the absorption. You're going to make some set of assumptions about what the other optical property is, so that then you can figure out what the extra unknown is. Because sometimes you say, well, I'm just going to assume that the arm is mu sub S prime is 1 e to our lambda to the minus 1.3. And that'll give you mu sub S for all those values, and then you can back out what the absorption is from your arm, from the total reflection measurement. So any questions about that? Yeah.
So when you said we fixed the G, does that stay the same the entire time, the G? Like it doesn't matter what medium you're looking at, or is the G is it okay to keep it at a specific fixing G? I just
Yes.
don't know why you would fix
Yes.
it. Yeah.
Setting G to, so you have a whole spectrum of measurements, right? You have over from visible to near infrared. And you can say, oh, G is 0.9 for all of those. And you're going to end up being pretty close. That G doesn't tend to vary that much. Working with tin, we're doing microspheres. And because we knew that the scattering of the microspheres was changing with wavelength, right? The size parameter changes, therefore the scattering coefficient changes, and the anisotropy also changes. So we were able to, you can put in a different value of G for every one of your observed values. So sometimes it's worthwhile to allow it to change, is what I'm saying. Most of the time you can just say 0.9 and then.
Yeah, I just want to add to that is when you use something that you know that you can simulate, like a microsphere. What I did was I basically simulated using the mean scattering that you guys probably did in day 2 or something. Basically take that whole curve, both G and also the mu that you got simulated as kind of like ground truth, put the G into IID and see if I can get the scattering value out to be at roughly the same as the simulation.
So to be completely transparent, he was doing this because he had troubles. Lots of troubles. So it can be, you put in what you know. That's always the case. You try and put in as much of the physics that you know of the problem before you solve it. Oh, you're just going to you're not asking a question. You're handling the mic. Good. Okay, so sphere stuff. Integrating spheres. How many have used an integrating sphere? So what's the basic idea of what an integrating sphere? Yeah, and it integrates what it and
Uniform illumination along the whole sphere.
that give the man a PhD. The idea is that the light goes in, the walls are white, they'll bounce, the light coming in will bounce around many times. Because the surface is Lambertian, it reflects uniformly in all directions. And so if the sphere has a reflectivity of 0.99, then it's going to bounce around on average like 50 times before it ends up being absorbed. And so what happens is that means that every place on the wall has the same amount of illumination. So maybe this, So here I have a picture of one of the ports on an integrated sphere. I've just taken a Heaney, hit one spot on the wall. So, and then I'm looking into the sphere, and you see that they're speckled, but it's uniform, and and so that's the whole idea, is that all the light that gets into the sphere bounces around, becomes uniform, and the amount that hits a detector, this could be covered by a detector, it's going to be directly proportional to the amount of light that was put in. So if we have a sample, we have our beam coming in, hits a sample, light bounces around, and because all the light that comes off the sample bounces around many times, that means your detector is measuring something that is proportional to the total reflection from the sample. Now, a detail is that you can have your beam come in. You have your sample, it's sandwiched between glass slides, they're nice and flat. And you'll have a specular reflection, and that'll hit the wall, and that's great because it stays in the sample, and so all the scattered light bounces from the walls, and all the unscattered light also bounces from the walls. And so you get something that's directly proportional to the total reflection. However, if you come in at a slightly different angle, and your entrance port is big enough, this light can leave. And so this, you say, well, it's only 4%, right? And it turns out that if your absorption is kind of high, then that 4% is larger than your diffuse reflection. And so you have to know what's going on in your sphere or during your measurements, whether you're collecting the unscattered light and similarly the unscattered transmission. it's not such a big deal for the transmission. But and the inverse adding doubling can accommodate both. Now, I said that I lied earlier. I said that the light going into the sphere, it bounces around a reflection. It's directly proportional to what the detector sees on the wall. And this is good. So here we have a 200 millimeter sphere, a good sized sphere, wall reflections of 98%. And we have different port diameters. And so there's different amounts of a large port, more light can leak out. So it doesn't do as many bounces. And if you have a small ports, then it is directly linear. But as the amount of the fraction of the wall that is no longer Lambertian and highly reflective gets bigger, then it becomes nonlinear. So bottom line is you should be aware of this. You don't have to worry about it because it's all taken care of inside that inverse adding doubling program. And there's equations for this based upon the area of your sample, the area detector, the wall reflectivity, the area of your entrance. It's things that you have to measure. So you're going to have to measure all your port sizes, and you're going to have some idea what your reflectivity of your sphere walls are. So the world of chemistry has known about this for some time, and they have said, oh, well, you should use a dual beam system. So here, what you do is you have one beam goes in, hits the sample, the light bounces around, and you make a measurement. And then you switch to there's some sort of mirror here that changes the direction, and the light will now hit a standard, and the sphere is exactly the same. It has the same amount of losses. And so when you divide these two, you get an accurate value for your reflection, and you don't have to worry about any of these sphere corrections. So some of the most impressive measurements I've seen have used a dual beam system. So this is another geometry where instead of them both coming in through the front, here you have your sample. I don't know, there's a monochromator that switches between each side. It goes through a sample, hits sorry, this is a lens. So hit your sample, and in one case it hits it directly, the other case it bounces around and then it hits reference standard. Most spectrophotometers with built-in integrating spheres use this method. So if you are ever mucking around with integrating spheres, you'll note that there are these port covers. And if you look at the port cover, you see that there are set screws, and these set screws are insanely small. And so the Allen wrenches are insanely small. And my recommendation is put a piece of tape on them with the size so that you don't lose the silly things, because it turns out nobody else in the building has a 0.0035 Allen wrench. This SMA port is handy because if you're doing everything fiber-based, then you can just screw your fiber in. You have a large 1 millimeter fiber, and it is held in, and the rest of the inside of this port cover is all white, so it's highly reflective, and then you only have losses for the face of the fiber. Thin and grainy spheres are ridiculously expensive. And they've always been ridiculously expensive. And what I can tell you is making your own integrated sphere is not worth the expense. It's a painful, painful process to put paint barium white on the inside, or it's you can make your own sphere. It's just at the end you have a sphere that is constantly falling apart. So when I show you the spheres are usually this way, and your sample goes here. But I've found that having the sphere mounted so that the sample can be on the top works really great. It means that you don't have to figure out how to hold the sample on. For a whole variety of reasons, it works better. The only downside is if you have members in your lab that have gooey things, and then the gooey stuff drips into your sphere, and your very expensive sphere, then you're very sad. So sometimes you want maximum signal to go in your spectrometer because you don't have so much light coming out of the sphere because it's been bouncing around. So it's significantly less. So if you have a port, this is just to tell you that your geometric optics classes were not wasted. You want to match the F number of your port to the F number of the spectrometer, so that this angle match. So this is basically determines the F number, the cone of light that makes it around, hits the grating, bounces, and gets to the detector. Light that is coming at larger angles just becomes noise in your spectrometer. Oh, thank you. I could have mimed the rest of it too. So match your F number if you're using a spectrometer. And so this is what it looks like. Here's the sphere. Here's a port. You set the size of the port, and then you change this distance so that it matches the F number of the spectrograph. Another way you can do the measurements is you have fixed, usually what I'm going to show you later on is if you're doing reflectance measurements, you have the light go in, hits the sample, and then is collected by the sphere. Then you move the sample to the front, and then you have the light going in, hitting the front of the sample, and you make your transmission measurement. Another way of doing it is to have two optical fibers. So you have one inside the sphere that illuminates, that you set it so that the spot is exactly the same as for the transmittance fiber. So when this one's on, you're making a transmission measurement, and when this one's on, you're making a reflectance measurement. What does this look like? You can sort of see, here's the transmission fiber above, and here's a reflection fiber where I have carefully painted the thing with barium sulfate. Did I say everything I wanted on this? Use big fibers, 1 millimeter fiber. You paint the reflectance fiber, and you need to calibrate your sphere again because we've introduced this white thing that should have really high reflectivity, but that's another way that light can be lost. And that the only way that light is lost in this sphere is either through the port sizes, which you've measured and you can't change, but the wall reflectivity also is the primary loss. And so if you change anything in the sphere, if you paint a part of the sphere black, you're going to need, the overall wall reflectivity will change. And so you do that to the fiber. So as you know, absolute measurements are much harder than relative measurements. This is why NIST has an entire institute to do an absolute measurement. The relative measurements, you go, well, I got my light, I measure it, it's like 1 watt, and then I make my reflection measurement, it's 0.5 watts. My reflectance is 50%. Pretty straightforward. But knowing that that is 1 watt means that everything has to, you can't have any losses. Your detector has to be exactly calibrated. It's much, much harder. And so you have to use relative measurements. So you need to make 3 measurements to come up with your relative reflectivity. Here we have an empty port. Light goes in, it's a standard. This is a known standard, so we know what the reflectivity of the standard is. It's our standard. Here we have our sample. The light goes in, it bounces around, and then we can make the measurement of the reflection from the sample. And then finally, we open up the back ports, the light can go directly through. And you would say, well, this is a stupid experiment, right? Nothing's going, but it turns out that real life seldom matches my drawings. And the beam here isn't always a laser beam, but it's a beam that's expanding. And so you'll find that there is some amount of light that will hit around the port, which has to be subtracted off somehow. It has to be accounted for. And so you make these 3 measurements at every wavelength, and then you can figure out what the relative reflection is at every wavelength. There's a set of 3 measurements for the transmission. There's the light just going in, hitting the back wall. You got your sample here, so that's a transmission measurement, and then you block the beam. And you say, well, that's another stupid experiment, because if you block the beam, nothing's going in. But if there's dark noise in your detector, it has to be subtracted off some way. The unscattered transmission, I'll talk a little bit about that. It's hard to do for a variety of reasons, and that's that you have scattering in all directions, and then you have this unscattered that goes straight through. But that unscattered fraction may be 0.1%. And these will all be relatively high. So if you have a sample that's white, then this could be 50%, and this is still going to be 0.01. So you're trying to measure this 0.01 on this background of a large amount of diffuse light that's scattered. So what you can do is use the fact that the laser beam does not diverge as fast as a Lambertian. And so you move this aperture far enough out so that the solid angle collected by this detector is small enough that you're able to measure the very small amount of collimated light that comes through. So these are the 3 measurements you might make, and don't do it, is my unless you absolutely have to, because if you have a laser beam, then you're going to end up having to worry about speckle. If you have any, and it's just a very, very hard measurement to do. And at the end, you're going to get G is 0.85, and you could have just put in G equals 0.9 from the start and saved yourself 2 weeks of your life. So IAD is written in C for speed because C used to be the only language that existed. There's a new, not quite finished version that's fully written in Python. There's a zillion options for the command line. You can say, you can specify the sphere parameters. You can say, oh, okay, I'm going to just assume the albedo is 0.4 for all the samples I'm doing. And there's, this goes up to Z. So there's a bunch. And then, but I would point out these two, this one in particular, the fraction of unscattered reflection in the reflected measurement. And so if you're not collecting that light, if it's bouncing directly out, you need to set this to 0. Otherwise, the program assumes that you're collecting all the light. Bunch of example things. So how does this work? IED is the name of the program. -R says that's give me a value for m sub r. And then you put in 0.6. And then what's it going to do? Well, it assumes that without giving another value, that the thickness is 1 millimeter. You can specify that on the line, but I'm too lazy to type it. And it'll assume that the anisotropy is 0. And it will assume that scattering coefficient is 1 per millimeter. And so you do this, and then what it comes back with is it shows you that your measured reflectivity was 0.6. The fitted value is 0.6. That's great. There's no transmission measurement, so we just assume that it's 0. The fit to the transmission turns out to be 0 as well, 10 to the minus 13. Then we have the absorption coefficient. It reports a absorption coefficient. And then you see here that the scattering coefficient was assumed to be 1. And here G is given as 0. So it's just making reasonable values for the defaults. If we have 2 measurements, we have relative reflection, relative transmission. This -V0 says don't write a bunch of stuff to the screen. And here you look at the output and you see your reflectivity, the fitted reflectivity, the transmission, the fitted transmission. And now we can get both absorption and scattering, and G is assumed to be 0. And here you just say, oh, well, if I change the thickness to from 1 millimeter to 1/10 of a millimeter, that means that my absorption and scattering have to increase by a factor of 10. Here it's 2.05, 0.25, 0.2, just say, for absorption. And now it goes from 0.2 to 2 as we've changed the thickness of the sample, because the thickness only comes out at the very end. It's not, internally it does everything in non-dimensional units, and so yeah, you can scale everything. Here's how you specify different anisotropy. You just put -G and 0.9 on the line, and then you see that this is, and then our scattering coefficient has changed again by a factor of 10. And if you're lucky enough to have an unscattered transmission measurement, then it will again show you the fitted values, mu sub A, mu sub S, and the anisotropy. And sometimes anisotropies come back as negative. Tends not to be, usually when it comes back negative, that means you screwed something up. So far we've assumed these slabs are, we have a slab with an index of refraction of 1, and we're measuring reflection and transmission from that. But in reality, the slabs don't have an index refraction of 1. They have an index refraction of 1.3 or 1.4. And here we see that the absorption and scattering, the derived absorption and scattering changed dramatically because of the the mismatched boundaries. And we can do it go even farther is we can put our sample between microscope slides. The microscope slides have an index ratio of 1.5. So we have this sandwich, and then we can calculate what the, yeah, this says that we essentially have no slides. And you can see that there's very little change in this case between having slides and no slides, because the glass doesn't affect things that much because it's pretty close to the index refraction of the slab.
And all this, are you assuming that the Fresnel reflection is measured or not, or zero?
So
Like with those prompts that you have there.
yeah, so in here you do the Fresnel reflection at all angles
I'm sorry, I mean,
For-
like just like basically from the surface, from the top surface.
from the top surface,
Yeah, it's the-
whether you include the specularly
Yeah.
reflected stuff. These all include it. If you want to not include it, then you put -C0 after
Okay.
it, and then it doesn't include it. But more commonly is you've made this whole spectrum. You're not going to be typing in all the data points yourself. You're going to be like, you just give me a file and invert the file. And so that's supported by, I've chosen RXT, but you can name it whatever you want as long as you tell it what the extension is. There's some weird possible cases, especially if you have the geometry with the sample on top, because usually you have the light hits from the same direction. So the reflectivity here and the reflectivity here are slightly different. So they're different orientations, and you can handle them all with different options. And finally, this comes from some of the goniometer work. This is for a quite thin sample, 280 microns thick, so it's very thin. And you see this is dermis, and you see that the unscattered amount of light relative to the scattered light that we've fit to the to a Henny-Greenstein phase function in this case, but that the scattered light is essentially equal to the unscattered light in this case. And that's when you have a 300 micron thick sample. If you have a 1 millimeter thick sample, it's going to be impossible to distinguish from the background. So at one point in my career, I said, I can support graduate students by making phantoms. Stupid idea. But, if you make phantoms, the people who get the phantoms want to know what the optical properties are. And so this is polyurethane. This is the way you can make the mixture is you have the polyurethane has two parts, and you can put the scatterer in one part and the absorber in the other part. And then you mix these up, then you mix the two together, you put it in a vacuum chamber to pull out the bubbles, you degas, and then you pour in a mold, and then you have a set of phantoms. And what my student Villa discovered was that if you take part A and add it to ink, or if you take part B and add it to the ink, right? So in this picture, our scatterer is titanium dioxide and our absorber is India ink. So it should be, you could add it, should be able to add it to either. And what he found was that the phantoms are completely different. And in fact, here he poured one where the India ink was put in part A, and here it's in part B, and completely different properties. It has exactly the same amount of ink, has exactly the same amount of scatterer, Same formulation, same amount of polyurethane, very, very different. And if you do measurements on each of these sides, you can do measurements on this side and that side. And then if you plot them, what you find is that on one side, it's constant. There is no dependence on absorption with wavelength. It's a neutral density filter. And the other side, this is what we would expect, is we expected that the absorption of the ink would drop as you went into the infrared. And in both cases, you get the titanium dioxide values, the scattering values from the titanium dioxide. Or no, the absorption values from the titanium dioxide. So the moral of the story is if you're ever making phantoms, you got to worry about aggregation. Aggregation happens when particles collect together. This can happen to blood samples. You can get your red blood cells. If they're the right age, they'll just start stacking together and they'll make these large roulettes that are rouleaus that are in your sample. And so you'll have a very different microstructure than you had before. And again, we're assuming everything is uniform, that there is no variation with for each particle. And so what happened is in the neutral density filter side, we get these aggregates. And if you look at it from the top, they're so dark that no light gets through any of these. But the rest of the light gets through fine through the non parts. And that was the more transparent side. Whereas if it was uniformly diluted, then you would get an average value over the whole thing. So instead of getting 0 and 100%, you get some fraction in between. This is important for melanosomes, for example, because melanin content is not spread uniformly. We can talk about melanin dust, but in general, the melanosomes are very, very dark and no light gets through them. And they're going to act much more like a neutral density filter than like a uniform absorber. So they've got a whole drawers full of these things. When you specify, our values will be within 10% of what the customer spec'd, and it's not within 10%, then you have to do the whole thing again and you repeat. So, and there's all sorts of subtle things you have to do to tweak but overall, I had to improve the accuracy of how the inverse process was done because, I was saying it needs to be with an absolute accuracy of 5% or something. And so I needed to figure out all the experimental details that would affect that value. And a really important one is to measure the sphere wall reflectivity. And the way you do this is you send light in and it hits the wall and you have a standard in the port, and then you have the light hits the wall without a standard in the port. And that the difference in what the detector sees is related to the wall reflectivity. But since you're making this small change, it's a difference measurement. And so you have the diffuse measurement with a standard and diffuse measurement with nothing. And then if this is small, then this becomes large and it's a hard measurement to make, right, Tin? But if you do make a good measurement of the wall reflectivity for your sphere, then you know that all the weirdnesses and how your detector is exactly mounted and how the standard or the sample is attached to your sphere is accounted for, and then you end up getting much, much better results. The other detail, which I ignored for a super long time, and this was done by one of my colleagues when I was in Amsterdam on a postdoc, so it was a zillion years ago, like 1988. And he did these measurements with a dual integrating sphere system, and he measured R and T, and then he added them together, and then he plotted this versus the thickness of the sample. So first thing that you notice is that R plus T is greater than 100. And you go, what's going on here? And then you see that, and so this has a relatively large port diameter and a small beam. But if we have a smaller port diameter and we have a larger beam, then you get very different results. And so all this means that the sphere parameters have to be worried about so that you get the right answer. The other issue is that if you have two integrating spheres and you're trying to make reflection transmission measurements at the same time, I suggest that you always use one sphere and do a reflection measurement, then do a transmission measurement. But if you're trying to measure something that's dynamic, you need to measure them both at the same time. And so you'll have two integrating spheres next to one another. Your sample will be placed in between the spheres. And we have our light come in here. We are collecting all the light that comes back into the sphere, but you notice that there's light that's going to go other places, right? And all this light that leaves elsewhere turns into absorption when you do the calculation, because adding doubling does not know anything about finite size samples. There are infinite samples, and the idea is that your ports are very big, your beam is very small, so you're collecting all the light. So what to do about this? Another example is here we have the fiber inside the sphere, the light comes out, and it will be directly lost. But you can always go with larger port sizes and have smaller beams to eliminate that sort of loss, right? As this beam gets very small, and assuming that the mean free path for scattering is high enough so that it doesn't, light cannot propagate, you basically have your glow ball that's right here, and very little gets out. You can fix it by using bigger port sizes. Unfortunately, remember the integrated sphere, its whole purpose in life is to bounce light around inside. And so all this light that is reflected goes into the rest of the sphere, and then it's incident on the sample again. So what you notice is that there's always going to be diffuse light across the whole sample, and most importantly, there's going to be diffuse light near the port edges. So this diffuse light hitting near here has a good chance of escaping. So you're always going to have to worry about this diffuse light loss. So what did I do? I said, let's just slap a Monte Carlo simulation on it so that we can estimate how much light was lost. So now the idea is that we do that iteration, we come up with some optical properties, we do a quick Monte Carlo calculation using just the final properties to figure out the lost light, put that back in, recalculate, and see if we get the same thing again. And so you do it until the optical properties don't change. So if we have, so this is an example of a 10-inch sphere with a 6 millimeter port. And I think that the beam size was 2 or 3 millimeters. And if we just do measurements and we don't include we only include the sphere corrections. I told you about all the sphere corrections that you have to worry about. And we just do those. Then we get, I don't know, an absorption coefficient of 0.3. Unfortunately, our dye, we know the absorption coefficient is this dashed line down here. So if we add one Monte Carlo correction, then it drops down to here, and then that's not quite enough. So you do it again because the optical properties have changed, and you do it again, and then you find, and you get so that it approaches the value of the absorption in a pure medium with no scattering around. The absorption peak almost certainly changes because this is in polyurethane rather than the solvent that it was in the spectrometer. If we use a bigger port size, something that's no longer 6 millimeters, but we choose a 1-inch port, then we do 2 sample thicknesses to make sure that things are working out. We find that the scattering coefficient and the absorption coefficient are identical for both of these. So this is just accounting for the sphere, and yeah, I don't want to talk about that. You can make it better and better, basically. So if you want to know more, you can look at the manual. So I wrote this, I don't know, 15 years ago. And since I'm just writing it for myself, as far as I know, nobody else is reading it. You know, I titled it Everything I Think You Should Know About Inverse Adding Doubling. The problem is that now people publish papers and then they refer to this in their bibliography, and then there's a stupid title in it. I'm like, this is just embarrassing. So don't make the mistake of coming up with a clever title if you don't want to see it in somebody's bibliography. So overall, adding doubling is good. It's a solid solution to the 1D problem. You can combine these, and it's been used many times with success. The reality is it does not always match theory, and so you have to make accommodations. And there are many, many tricks for making it more reliable. And if you see somebody who just did an inverse adding doubling experiment, the way to cut them off at the knees is say, so did you do the same experiment for a sample that was twice as thick? Because getting a result for one thickness is easy, but doing it for another thickness is also easy. But whether the intrinsic optical properties are the same is really, really unlikely. So you can always ask for multiple different thicknesses, different physical thicknesses. The other way to look at it is you see an absorption spectrum and a scattering spectrum. And for tissues, if the scattering spectrum is nice and monotonically decreasing, you go thumbs up. If you have a strong absorption peak, say you have a water absorption peak, and then you're looking at the scattering spectrum, and right where the absorption peak for water is, you see a dip in the scattering, you go, oh, they have not made their measurement properly, because these two things have to be decoupled. There's almost never a case where you have anything other than monotonically decreasing scattering with wavelength. So questions.
Have two questions. So first, what is the underlying model for the IAD? We're
Adding
using-
doubling.
I mean, how do we simulate the scattering using the delta P1 approximation, or there's a difference?
No, so adding doubling, if you do, the smallest you can do is n equals 4, which is the delta P3 approximation. So it includes 3 terms in the Legendre polynomial. So, the other thing is the adding doubling only does one-dimensional problems. So
Okay.
you can do the forward calculation simple enough. You just tell it what the scattering and
Okay, thanks. Another question, maybe not directly related to this, but how about we have a sample that is a combination of different components with different concentrations, and by measuring the total reflectance spectrum, could we further decompose it and guess the concentrations if the scattering parameters are known?
in principle, yes. The problem is that now you have a minimum of 4 unknowns. You have absorption scattering in the top layer and absorption scattering in the bottom layer. So that means you have to have 4 measurements to be able to figure these out. So the simple thing to do is to do each layer independently, then measure the absorption and scattering in each layer. Then you can put them together, and adding doubling will allow you to add those 2 layers together, and then you can see if that your samples when put together can be combined without interfering with one another. If you're doing skin and you have an epidermis and a dermis, and you're worried about the melanin or you're worried about blood, you're stuck because you need some way to probe. And so if I had to do it, say I was doing blood, I might put a bloodless epidermis in, kind of know what the optical properties of the bloodless epidermis, and then I'd just be determining the optical properties of the second layer.
Thanks.
Yeah.
And maybe another quick question. So, like, since let's assume that Monte Carlo is fast enough, and how would you comment this method comparing to use Monte Carlo to guess?
Not my problem. That's how I would say it.
Okay.
Somebody else is the guardian of the inverse Monte Carlo stuff, and I'm sure they're willing to help you.
Right.
I think they work fine.
Okay. Thanks. Yeah.
So maybe related with the second question by Michael, when you have the layered tissue, could it be possible to use 2 different spheres with 2 different sizes or port diameters to decouple the optical properties?
Yes, you can use 2 different size spheres. The sample, the ports on the sample should be the same size.
Okay.
So, you can't have 1 inch on one side and half an inch on the other side.
Yeah.
Yeah, almost nobody has bought two identical spheres because you don't have, except for Tim, yeah. Good, it's lunchtime then. There's no lunch, yeah. Oh, I was going to say,